All right, so we are now at section 2.32 talking about the marginal Gaussian distributions. So before we get into it, one kind of definition that I want to make sure you're clear on, which I heard a lot, when I was first starting, when we hear it all the time, and it's just, it can be a bit confusing, but it's just very simple. This idea of this marginal distribution. So the marginal distribution is we always talk about that in the context of a joint distribution, just like we're doing here, and it means nothing more than the distribution over a subset of the variables. So whenever you hear marginal, it just means a distribution over a subset. And we already talked about this in one of the earlier sections in chapter 1. But the idea is, if you have a probability distribution over, x and y, then you can talk about what is the distribution over just x. And the way you get that is by just integrating out the other variables, and you get what's called a marginal distribution, in this case over x. And you could do the same thing and get a distribution over y. And as we talked about before, the reason why we call it the marginal distribution is, if you look at, let's say this is like our p of, this is x, this is y, this is p of xy. Well, now if you integrate, that integration process, so this thing that we did where we said dy, that's just like the same as summing up the probability of this joint distribution across, across this grid and looking at what the distribution is that shows up on the margin. So it'll be something like that. So this here is going to be equal to px, which is going to be the integral over y, which is, which will just reduce this joint distribution that's defined over, this grid to something on the margin. And you can do the same thing in this direction as well. So that's at least how I remember it as being called, why it's called a marginal distribution. But the idea is just don't get confused by it. It just means when you have a joint distribution, the distribution you get when you integrate out a subset of the variables to get the marginal on the remaining. Okay, so now what flavor of this are we actually dealing with here? The flavor we're dealing with is we are talking about a joint distribution that is Gaussian, and in the previous section we looked at what happens when you condition on a particular value of one subset of variables. And we saw that it was going to be Gaussian. Now our question is, what about the marginal distribution here on a subset? So we're not conditioning anymore. We just say, look, you're giving me the joint distribution. What does the distribution over just a subset of them look like? And indeed, we have to, this is just, I guess, the sum rule of probability. And the cool thing, and maybe intuitive thing, but something we have to show, is that the resulting distribution is Gaussian. And not only is it Gaussian, it's going to be a particularly intuitive Gaussian. So this is going to be an easy one to remember in the result of. And the whole game is going to be the same one as before, which is going to be about completing the square. So you can always just go on, given this joint distribution, you can always just go and directly integrate it. But because things are Gaussian, we can use some of the nice properties of Gaussians to kind of avoid having to do any integrals directly and just essentially read off the terms. Read off first that it's going to be Gaussian, and second what the mean and covariance are. Pretty much the same way as we did before, using this idea of completing the square. So let's see how it's done, and it's, to go through it, it's still, it's still a bit of you have to be careful with the little calculations. So it's again important to see, what the technique is that we're using here, how we're using completing the square, because it's quite useful, and it'll just save you a lot of work in your own calculations later on. Okay, so let's before we get into it, let's just write down kind of what we're given. So we've got this idea that we have a joint distribution that is Gaussian. So let's just kind of write that out. So the idea is, let me switch pens here. So we've got, I'm going to start writing at the top, which you guys can see. Okay, so here we've got, generally a vector, and it's going to be actually decomposed into x of a and x of b. So these are our variables, and these can also be vectors, so just smaller dimension vectors. And now we're given that the joint distribution is Gaussian. So we've got means for these variables. So we've got the mean, which is going to be mu of a, mu of b, and we've also got the covariances, and this is the covariance of the A part, the covariance of A and B, covariance of B and A, which is just the transpose, covariance of B and B. And also importantly, we've got this precision, which is just the inverse of the covariance. And it also has its corresponding parts. And remember, the important thing to remember is that in general, this is BB. So in general, you can't just invert this to get that, right? So in general, there's actually a more complicated formula we saw before, the Schur complement that's related to that, which tells us how to get, for example, sigma AA in terms of all these covariances. And in general, they will all you will need all of these values to actually figure out, for example, this precision. So in general, sigma AA does not equal to, so you actually have to kind of work it out. And in the previous section, we did work out what the actual answer is. We're using one of these matrix identities, and we'll use that answer later on here. Okay, so now now we're told that this joint distribution is a Gaussian. So let's write out what that means. So we know that P of X is going to be equal to, and I think it's D over 2. D is the total dimension of X. And we won't need this part, but we'll just write it out anyway. This is our covariance, determinant of the covariance, the power of D over 2, I believe. Anyway, you can look up exactly what it is. The important part is going to be the exponent of minus 1/2 of X minus mu. So this is, again, this full, we're talking here about the full variables and the full means and the full covariance, times minus 1 X minus mu. Okay, so that's the probability distribution. First, we'll just replace this covariance, the inverse of the covariance, with the precision. So we just put in the precision there. And now we're going to, because we're going to be integrating, we want to split it up into its component parts. We're going to write this as, again, it's going to be that constant term at the beginning times the exponent. And the star of the show is going to be these terms inside this quadratic form inside the exponential. So it's going to be, and if you actually expand it out, we're going to see it's going to be minus 1/2, and it's going to have 4 parts, right? It's going to be X of A minus mu of A times sigma lambda AA, plus there's going to be X of A minus mu of A transpose, and now it's lambda AB, and you can see that you can kind of check that you're doing things properly, because the A here matches up the A's here, and then the B's matches up the B's there. So that's just the way it has to work. Plus XB minus mu of B transpose mu BA, XB minus, see, I can already tell I did it, mu of A, plus XB minus mu of B transpose BB, XB minus mu of B. Okay, so, and now we've got this really, so now what we want to do is we arrive at this part, right? We want to actually integrate this complicated expression. We want to integrate out X of B. And you can always go ahead and just do that integration directly, but it can be a bit complicated to do. And we want to use the fact that we have a Gaussian to kind of make our life easier. And basically the idea with doing that is to notice that whenever we have, whenever we see terms like this, we can just notice that, well, that is just the quadratic form part of the Gaussian distribution. And if we integrate over that, we know that it's just going to be 1 over this thing. So it's just going to be 1 over this normalizing constant, and the normalizing constant only depends on the covariance and not the mean. So essentially the form is, we're going to be massaging this expression, rearranging this expression, so that we can collect all of the XB terms into a form like this, and then we can just say, okay, well, we just integrate those out. I don't even have to worry about those, because when I integrate over xb, that's just going to disappear, leaving me with some term that looks like 1 over this component here. And so you'll see what that means. So it essentially just saves you a lot of direct integration. Okay, so let's see how he's going to talk about it. So the marginal distribution, exactly. So once again, our strategy for evaluating the distribution efficiently will be to focus on the quadratic form in the exponent of the joint distribution. So it's going to be this thing. So we're not going to integrate things directly. We're just going to focus on this part. And thereby to identify the mean and covariance of the marginal distribution P of x of a. Okay, so now it says the quadratic form for the joint distribution can be expressed using the partition precision matrix in the form 2.7t. So this is that's what we're talking about there. Because our goal is to integrate out xb, this is most easily achieved by first considering the terms involving x of b, and then completing the square in order to facilitate integration. Okay, so essentially it just says what we want to do is we want to get rid of x of b. So let's just look at this big expression we have and just collect the terms that we have that looks like that involve x of b. And then then what we'll do is, if we get it into this kind of form, then we can then rewrite this as just this expression plus some terms that don't have x of b in them. And you'll notice that m doesn't have x of b in it. And then this looks exactly like that, right? So we'll know that we can just integrate this out, and we'll just have some constant term that only depends on lambda b of b, because that's essentially what's showing up down there, and it won't have any x of b's in it. So we're trying to get rid of x of b. And the way we're doing that is by just completing the square and noticing that the quadratic form that we have is precisely the one of the Gaussian, and that when we integrate over it, when we actually do this operation, those terms will disappear and we'll just leave some constant term, some constant that doesn't involve x of b, and then we can just deal with x of a. So that's the whole game. Rearranging the terms so that we essentially, when we do this integral, we can just forget about x of b because it'll be integrated out, leaving us with the terms of x of a. Okay, so let's do that here. So let's write that out. So here, let's just see where he's getting all of these. So right now he's just saying, look, if we have something of this form, then we can actually just rephrase this as, and if you actually expand this out, you'll see that it is indeed the case, as x of b minus the inverse of this precision times the precision, etc., plus this additional term. This is kind of the completing the square part. And this m is going to be defined in this way. And the reason why we get this is by just, so how do we arrive at this particular expression? Well, we have to go all the way back up to this one and pull out all the terms that involve x of b. So let's just do that. And we'll see, okay, so we're going to get, there's going to be one term, let's just use different colors. So there's going to be an x of b multiplying lambda bb times x of b. So that's going to, and notice there's a minus 1/2 on the outside. So that is going to give us this term. So that's all and now we just want the terms that are linear in x of b. So let's use a different color. Let's use light blue. So let's see, what do we have? So we've got x of b transpose times this whole thing. And we'll have the same thing in transpose as well. So so essentially that will just turn this minus 1/2 into a minus 1, because we've got the same thing, but you see kind of happening in reverse. Okay, and so if we've done everything correctly, so that should give us x of b transpose m, and it should give us the linear terms. So let's make sure that is indeed the case. Let's see, what do we have? Oh yeah, and we forgot one term, and the other term is going to be this multiplying this, which then multiplies x of b. Okay, so let me just put that in green. So this is the green term, which is going to be multiplying that, and then we have the cyan contribution. So this is going to be coming from the green term, and this is going to be coming from the cyan term. So that's those guys. And the reason, and one other thing to remember is that this green term is going to be happening twice. So there's going to be the other side as well. So this multiplying this, multiplying that. So you can already tell, like, you have to, it's kind of a detailed calculation. There's nothing difficult about it. It's just a bunch of algebra. So you just have to make sure you have the right, you're just collecting the right terms, the right number of terms. But there's nothing fancy going on here. All we're doing is we're just expanding this and just collecting our terms that are quadratic in x of b, and then the linear terms in x of b, and it will turn out that the quadratic terms look exactly like this, and the linear terms are x of b transpose times some m, and the m will just look like that. And hopefully I've showed you where the different parts of m come from. Okay, so we're just collecting the terms, and once we've collected them, then we complete the square, and we write this expression as, well, something in the square of something that looks like the quadratic form of a Gaussian, plus some constant term. And the important thing about the constant term is that this, notice, no x of b inside. So there's no x of b in it. It has mu of b, the precision of b, and it has x of a, but no b terms. And that's good because we want to just integrate b out. So when we compute the integral over b, all that we're going to really care about is just this term, because this is constant. We can move it outside of the integral of x of b. Okay, so we see that the dependence on x of b has to be cast into the standard quadratic form of the Gaussian distribution, corresponding to the first term on the right-hand side of 2.84. So that's this one. Therefore, when we take the exponential of this quadratic form, because that's, remember, this thing is sitting inside an exponential. Therefore, thus when we take the exponential of this quadratic form, we see that the integration over x of b will take the form of this, right? So we're just taking this thing, we're integrating it over x of b, so that's over that, and getting something that looks like this. And that looks exactly like what we do for a Gaussian, except that we don't have this normalizing term outside. So all that means is, because a Gaussian distribution is a probability distribution, when you integrate over it, it has to integrate to 1. That means that this component has to equal to z, where z is the normalizing constant of the Gaussian. Right. Thus, when we take the exponential, we see that the integration over xb will take the form so-and-so. And this integration is easily performed by noticing that it is the integral over an unnormalized Gaussian. And so the result will be the reciprocal of the normalization constant. So that's what we just said. And we know from the form of the normalized Gaussian given by whatever so-and-so that this coefficient is independent of the mean. So there's nothing that depends on m here. And depends only on the determinant of the covariance matrix, or the inverse of the precision. Thus, by completing the square with respect to xb, we can integrate out xb, and the only term remaining from the contribution on the left-hand side of 2.884 that depend on x of a is the last term on the right-hand side of 2.84. Because ultimately we want to be collecting the terms in x of a, getting rid of the terms that depend on x of b, and keeping the terms that depend on x of a to then give us a clue as to what that distribution is going to be. So the idea is that we just integrate over this part, and if we integrate it, we're just going to get the result of this is going to be some function of just lambda bb, and that's really important because if it was a function of the mean as well, it would have x of a in it, and if we want to then figure out what the form of x of a is, then we need to kind of worry about that. But it turns out that because it's a Gaussian integral, if we integrate it, the integral only depends on this precision. So essentially, then we can just ignore it. So we can essentially ignore that that component, and the only bit that we have to now keep from essentially this contribution is this part, because it has x of a in it, and that's what he says. So we can integrate x of b, and the only term remaining from the contributions on the left-hand side of 2.84, so this thing, that depend on x of a is this part. Okay, so it's the last term on the right. Sorry, it's the last term on the right hand side of. Sorry, so not that part. This thing, which is given by 2.85. Okay, so let's just see kind of what we've been doing. So we've been wanting to integrate over this whole thing in terms of integrate out x of b. And so what we did was we collected the terms that were quadratic and linear, because that's all you have. You have quadratic terms in x of b and linear terms in x of b, and we got this form. We completed the square on that to make the integration simple, to make this integration simple. And we found out, fortunately, that if you integrate over this, the result only depends on lambda bb, so it doesn't depend on x of a, because that dependence on x of a will only come through m. And so we said that, okay, so the only contribution, so the only part after we integrate over x of b, the only thing that's left that depends on x of a is going to be this component. Okay, so we still have to account for the terms that are that involve x of a, so that we haven't already included, but we have included some of them, the ones that also involve x of b, and the only bit that's left after integrating out over x of b from that component is this. Okay, so that's all we've done here. Now combining this term, okay, so combining this term, so we're talking about this now, combining this term with the remaining terms from 2.70 that depends on x of a, we obtain this expression. So where is this coming from? Well, this is, let me just write this out. So this is just m. This is just m transpose. So the first part is just this, because we've already integrated out of that. And then we have the remaining terms that we haven't included. So we have the quadratic terms in x of a, which we haven't talked about because there were no x of b's in them, and there is this additional term that just involves the means, the two means. And now if you actually expand this out, and I did expand this out, and it is indeed the case, you end up getting an expression that looks like this. And let me switch my color. So there is here, now you have a quadratic term in x of a, and now it has a bunch of precision showing up in it. And now you have a linear term in x of a that has the same precisions, and then also the mean term, and then some constants that don't depend on x of a, and x of b is entirely gone now. Okay, so again, by comparison to 2.71, so now essentially what we're doing is we're just now going to compare to our template of what the quadratic form for a Gaussian looks like. And again, let me write that at the top. So remember, for a Gaussian, it's just going to be the exponential of minus 1/2 of, so if we have something like this, well, then this is going to be x minus 1/2 of x transpose sigma minus 1 x plus x transpose sigma minus 1 mu plus some constant that doesn't depend on x. And lo and behold, what do we have? Look, we have x transpose, so we've got x of a transpose times something times x of a, which tells us that so from this we can conclude that, let's call it, our covariance is going to equal to minus 1, just by reading it off, just by looking at that and comparing to this. And look, and then we've got the second term, which is x of a, again, terrific. And then look, fortunately, it's also multiplying this, so this is going to be sigma a minus 1. It's also multiplying sigma a minus 1, oops, times mu of a. So if we just compare these terms, if we compare that and that, so let me use a different color. Now if we compare this with this, we can immediately guess that our the mean of this distribution is mu of a, right? Because of what it looks like. So we first, and just to take one step back, this also shows us that the distribution on x of a is going to be Gaussian because we have this quadratic form. So we got the quadratic form, which tells us that it's Gaussian, and now we're just reading off what the covariance and the mean is going to be by just looking at this template. We're doing kind of a template matching. And so we end up with exactly this, that the covariance is going to be the inverse of this precision term, and the mean is just going to be, if you work it out, it's just, or just look at the template, this mean is going to be the mu of A. Okay, so that was really simple. And so now just the final step to kind of relate this, remember, so what is, in general, this looks like a complicated expression for the covariance of this variable. And notice, the thing to notice here is that this isn't, not yet anyway, we're just saying this isn't, so right now we haven't established that this is actually going to equal to the covariance of the A terms that we started out with back here. So we haven't established that it actually equals this yet. We've just said, look, we're going to integrate out the B. We'll get some covariance over the A variables, and we're just going to call it sigma A. We don't know that this is actually sigma AA that we started out with. And the way we're going to establish that is we're going to say that, well, it will turn out if we go back to our matrix identities. That if we look at the precision matrix, so it's, here we've got sigma AA, sigma AB, sigma BA, sigma BB, and we take the inverse, that gives us our covariance matrices, and this first covariance term is actually going to equal exactly what we have up here. So at this point, we establish that this is actually equal to sigma A. So the important thing to keep in mind is that up to this point, we have just found out that it's a Gaussian, it has some covariance, which is related to the precisions we started out with, and it has a mean, which is the mean of the A variables that we started out with. So the mean is the mean of the A component of our joint variable that we started out with. But the covariance is, it looks like it's just related to the precisions that we have, but it's related to all the precisions, right? The AA, AB, BB, BA minus 1. So it's you're just looking at that, it's not clear that this actually has any simple meaning in terms of the covariances that we started out with. But it turns out, if we recall how our precisions are related to our covariances, it will turn out that actually this expression that we have is actually going to be equal to sigma, the covariance of just the A components. So with making that realization, we arrive at this kind of very intuitive result that when you have the joint distribution, given as it was here, as we gave it here, well, then the marginal distribution on the A variables has the mean corresponding to the mean of those variables, and the covariance corresponding to the covariance, again, of those variables. And that kind of makes sense, right? The marginal distribution is, if I don't know anything about B, and I just focus on the A variables, well, the A variables are just doing whatever they're doing. They're related to each other the way that they are, and those relationships are given by the mean and the covariance that we are provided with. Okay, so we see that for a marginal distribution, the mean and covariance are most simply expressed in terms of the partition covariance matrix. In contrast to conditional distributions, for which the partition precision matrix gives rise to simpler expressions. So all he's saying is that, and we'll see it below, we already saw it in the last section, that it's, we get a simpler expression if we think about the marginal distributions in terms of the covariances and the means that we're given. But I think it's just ultimately that really kind of intuitive result that, you're given the joint distribution and you have the data on, how the marginal variables relate to each other. And if you only care about those, well, then you can just focus on this subset of the distribution, this subset of the Gaussian, basically. Great. So that's what we've just established. This is actually quite important. So let me highlight it. So this is really important. And we see that for the marginal, the mean and covariance are, etc. Okay. Good. So the last little bit is just going to be just summarizing the results from the last two sections. So given a joint distribution with let me switch to the laser pointer here, with precision is equal to inverse. So this is exactly what we had. Here is the means and the covariances and the corresponding precisions. The conditional distribution is going to, the mean is going to be updated in a particular way, and the covariance is just going to be the inverse of the precision. And for the marginal distribution, the mean doesn't get updated either. The mean is just the marginal mean, this thing, so no update, and the covariance is just the marginal covariance, which is this guy. So that's kind of a summary of the results. So again, the one that I would memorize of these two is actually this one. The other one you can just look up the formula for. Just remember that it will be Gaussian. If you have a joint Gaussian, conditioning on one of the on a subset of the variables will leave a Gaussian distribution on the others. And you can always look up. You can just come back here and look up what the expression is. But just remember the main, the key idea here is this idea of completing the square. That's kind of the key analytical technique that you can take away from this as well. Okay, and let's just have a look at these. There's a couple of pictures that we should look at, which are quite useful. So let me just zoom in, make sure you can see it. So what we've got here is going to be that we have a joint distribution. And this is on x of a and x of b. And the first thing we want to look at is the marginal distribution on x of a. So the marginal distribution is this thing. So we take this joint distribution and we just sum it. We just sum it across this direction, and we get the marginal. You can see that it's kind of centered at 0.5, and it kind of has the shape that you want. And the more interesting one is actually the conditional distribution. The conditional distribution in this case, given that x of b is equal to 0.7. So you can see that when you cross this line, you can probably guess that we'll get a distribution that looks like this. And when you normalize it to be to sum to 1, you actually get this conditional distribution. And kind of the intuitive notion here is that these two variables are positively correlated. So if I tell you that x of b is 0.7, that's going to shift the distribution on x of a. So your a priori, your prior knowledge on x of a says, well, it has this mean around 0.5. But now that I've given you that x of b is 0.7, the positive correlation between them gives you a posterior distribution on x of a that's shifted to the right because of this, this observation you have of x of b being equal to 0.7. So this correlate, and an interesting thing to notice is what would happen if they're independent. So if you look at what happens if they're independent, then actually we would have a distribution that looks like this. So this slanted Gaussian would actually look like this, something like that. You just imagine that it's flat. And now conditioning on x of b equal to 0.7, well, what would you get in that case? Well, you would get a distribution that looks like this, maybe, but even smaller than that. But when you normalize it to get the conditional distribution, you would get something that looks exactly like the marginal distribution. So in the case that they're independent, the marginal distribution would look like the conditional distribution because conditioning on b would tell you nothing about x of a. So you would end up in the same boat as the marginal setting. But in the example that we're given here, we have this positive correlation between the two variables, which means that me telling you something about x of b tells you something about what x of a is going to be, and therefore your marginal distribution does not look like your conditional distribution does not look like your marginal distribution. It's actually been shifted because of the evidence you've observed. Great. Okay, so I think that is all I wanted to say about this section. So I think it's a useful one to go through to get the hang of completing the square. It's very useful. I've used it lots of times in my own work. It comes up all the time. Gaussian integrals are going to be like among the simplest that you're going to have to deal with. It's really just useful to know how to do them and how to avoid actually computing them with techniques like this. And then also what the conceptual point here was that the marginal distribution, if you're looking on a joint distribution Gaussian, the marginal distribution is just like taking the corresponding mean from the joint distribution, the corresponding covariance, which is I guess kind of intuitive. Good. So I hope you've enjoyed this video. I hope you've learned something. Please let me know in the comments if you haven't, or if you have, and if there's something missing, if I've explained something incorrectly. I'd be happy to fix it. And otherwise, I hope to see you next time, where we'll be talking about Bayes' theorem for Gaussian variables. So hope to see you then. Thanks.